In this video, we're going to make some connections between the previous two videos, the chi-square goodness of fit test and the hypothesis test for one proportion, which utilizes the z distribution. So, namely, this is actually a video that connects the standard normal distribution to the chi-square distribution. It's kind of cool stuff. Well, to make this connection, I want to utilize a previously completed example that was from 2 videos prior. This was the nudibranch example in which, there was a sample of 580 nudibranchs and 41 of them had a mutation, and then we created a confidence interval for the population proportion that possessed the mutation. So we did the confidence interval, then we went through the formal hypothesis test process that allows us to claim that the sample data suggests that the population proportion is significantly less than 10% at the 5% level of significance. And so this was 2 videos ago. I'll put the link up here. And of particular importance is the test statistic from this hypothesis test. I'll go ahead and kind of put it in a circle here, because we're going to connect the result of this hypothesis test, which is founded on this test statistic, and we're going to connect that to the goodness of fit test. So essentially, we are going to redo this problem, which is about a dichotomous variable, but we're going to do it with a goodness of fit perspective utilizing the chi-square distribution. So using the goodness of fit test here for the same example, the null hypothesis would be that the probability of observing a mutant was 0.10, and therefore not a mutant probability, the complement to that. And then the alternative would be that the distribution of the mutation prevalence is different than that. To get geared up for the test statistic for this goodness of fit test, recall that we need to determine these expected values for the number of individuals with the mutant present under the assumption that is stated in the null hypothesis. So recall these expected values are just n times p. The value for the probabilities are stated here, and recall that the sample size is 580. That was from the setup of the nudibranch example, and that 41 were observed to have the mutation. So then the expected number of nudibranchs with the mutation in our sample of 580, if the null hypothesis was true, it would be only 10% of them, which is 58. And the number of nudibranchs without the mutation, complement 0.9, that would be 522. So just a simple n times p there. Oh good, it looks like the requirements for the chi-square goodness of fit test are met, since all of the expected values exceed 5. Let's go ahead and compute this test statistic. Because there's only 2 categories here, this will be fairly quick. The number observed with the mutation was 41, but if the true population proportion was 10%, we would have expected to have seen 58. And then we will subtract and square and divide again by 58. The next term here, the number observed, without the mutation, therefore, was 539. We will subtract the expected number, 522, and divide by 522. This results in a chi-square test statistic of about 5.536398. Why not hold on to all of those? Our next step, as always, is to determine the p-value for this hypothesis test. For this goodness of fit interpretation, recall that the degrees of freedom is the number of categories minus 1. So here, this would be, well, there was either the mutation present or not present. So that's 2 minus 1, which is a 1. And we want to find the probability that our test statistic is at least this value or larger. So we're going to use R to find this probability in the chi-square distribution. Okay, a probability is desired in the chi-square distribution. The chi-square value is 5.536398. Okay, comma, degrees of freedom. And we always want the area in the right tail for a chi-square distribution. See the previous video for notes on that. And so 1 minus for the right-sided area. Now, with the proportion test that we did in the previous video, right, we ended up rejecting the null hypothesis, small p-value. The chi-square approach here should result in the same conclusion. Possibly not the same p-value, but the same conclusion. A small p-value as expected, because we know we should be rejecting the null hypothesis. So even though these p-values are not the same, it's actually because the p-value from the proportion test was only one-tailed. And therefore we did not double this 0.009. However, you might be able to see that if we do double this p-value, if this was a two-tailed or non-directional test, then the p-value between the goodness of fit test and the proportion test, if it was two-tailed, would be in agreement. And so I won't restate in full depth the entire conclusion here, because that's in the previous video, but we do know that since the p-value is low, we reject the null hypothesis. Now, what is the connection that I want to make between these two tests? Not only that they resulted in the same conclusion, because based on a different perspective, but I do want to point out the connection in the test statistics. Now, it may not be clear at the moment, but I will hopefully make that clear. So I've got them both circled here. Okay, so here comes the connection. What we've been waiting for is that the chi-square distribution is equivalent to the standard normal z distribution, or the square of it, as long as there are only two categories. Right? That's why we were able to do this. If there was a third category, it's not going to work out so well. Let's look at the test statistic from the z-test, which was about negative 2.35. I'm going to hold a few more decimal points here. 2955. Now I'm saying it's equivalent to the square of the z distribution. So I'm going to square this amount. And let's do that in R. negative 2.352955, throw it in a square, and if these are equivalent, then this should equal the chi-square test statistic, which is encircled there. Yes indeed. So this equals about 5.536, which is the chi-square test statistic value for this example. So this is not really a proof, but hopefully a sufficient illustration that demonstrates that the chi-square distribution is the square of the standard normal distribution. Furthermore, we kind of did another example of a goodness of fit test with only two categories.